Okay, we have a quiz at the end of class today, and there's no lab. I will be available in the lab room for questions. So if you have any questions, come on in. I'd be happy to go over problems with you. One thing though, today I have to be out of here at 2:20. So if that doesn't work with your schedule, let me know and we can do a Zoom call or something. But I just have to leave at 2:20 today. So that's 50 minutes that we have if you want to work on stuff. Anybody have any homework questions you'd like me to go over? Okay. Let's just keep going with some conservation of mechanical energy examples. So let's say there's a skateboard. And it's heading towards this hill that has a height of 2 meters. And we want to know how fast does the person need to be at the bottom of the hill to be moving at 2 meters per second at the top of the hill. And then let's also figure out so after we do this, what's the total work done by gravity in this time? And let's give this person a mass. Let's say the mass is 40 kilograms. Okay. So one thing you really need to get used to is like how do you recognize problems that you're going to use conservation of mechanical energy for? The answer is it always has to be something where you're trying to relate a location to a speed. And you can see that part A is asking that. And then the other thing is the only forces acting during that time can be, like the only forces you can have to use conservation of mechanical energy is gravity, spring forces, normal forces in rolling and sliding, or centripetal forces in circular motion. If you drew a free body diagram of this person at any point during that motion, the only forces would be the weight force from gravity and the normal force from the ground. So this looks like a really good candidate for this, okay? It's relating speed to location, and the forces fit into that group of forces. So we'll set up instant 1 to be at the bottom of the hill, and instant 2 to be at the top of the hill. And I'm going to choose my h equals 0 to be at the bottom of the hill. Remember, you can always choose that wherever you want. You just have to keep it for the whole problem. So at the bottom of the hill, the gravitational potential energy is the mass of 40 times 9.81 times, what's the height at the bottom of the hill? 0. So So there's no gravitational potential energy at the bottom of the hill. And then the kinetic energy is 1/2 times the mass of 40 times the speed squared. We don't know the speed. We're trying to calculate it. So I'm just going to keep that as v squared. And hopefully we'll be able to calculate that in the equation. So if I simplify this, we get 20v squared. Then at the top of the hill, the gravitational potential energy is 40 times 9.81 times what's the height at the top of the hill? 2. And so this is equal to 784.8. And then the kinetic energy at the top of the hill is 1/2 times the mass times the speed squared. I said at the top of the hill, the person is going 2 meters per second. So this is 2 squared. And so we get 80. So this is in joules, this is in joules. And now I'll add up all the stuff at instant 1 and set it equal to the sum of the stuff at instant 2. So we have 0 plus 20v squared is equal to 784.8 plus 80. So 20v squared is equal to 864.8. Divide that by 20. And you get that v squared is equal to 43.24. And so v is equal to the square root of that. So 6.58 meters per second. And we want the positive because this is a speed. Any questions about that? Okay, so now that's part A. Now the second one asks, what's the work done by gravity? We've calculated the potential energies. So remember that the work done by a force, by a conservative force, a force that has potential energy, is equal to the negative change in potential energy. So this is negative the potential energy of gravity at the later instant. Minus the potential energy of gravity at the earlier instant. And so the work is equal to negative 784.8 joules. Are there any other forces that do work in this problem? Well, are there any other forces? There's one more force, the normal force, but the normal force in rolling and sliding does 0 work. So the only work is done by gravity, okay? Well, if the only work is done by gravity, then that's the only thing affecting the speed of the object. So does it make sense that from the starting instant to the later instant, energy is taken away from the object? Kinetic energy is taken away? Yeah, it starts out fast, ends up slow, and so you'd expect to have a decrease in kinetic energy. Okay? Bless you. let's do one with a spring. So this is not something I'm going to ask you to do in problems. I'm just going to tell you what the spring constant is. But I'm going to start this problem by just showing you how you would calculate the spring stiffness. So let's say that, so we have a, okay, I'm going to draw what's going on with the problem first, and then the second part will show how to calculate that stiffness. So let's say that that stiffness K is 400 newtons per meter. And the mass of this cart is 2 kilograms. And let's say that we pull the cart back 8 centimeters from its resting length, from the spring's resting length. And then we let it go. Okay, so we pull it back 8 centimeters and let go. And if you can picture what this system would do, this cart would get pulled this way. Then as it passed the spring's resting length, it would start to slow down. Then it would go this way until it stopped, and it would just oscillate back and forth. And the middle of that oscillation would be the spring's resting length. Okay, so let's calculate what's the speed of this cart when it passes the spring's resting length. Okay, and I want to point out that that would be the speed whether it's passing this resting length going this way or on the way back going this way. There's a perfect symmetry to all that. It's just going to be a sinusoidal oscillation. Okay. So what's the speed of the cart when it passes the spring's resting length? Okay, so again, let's think about how suitable conservation of mechanical energy is for this. This problem is asking for a relationship between a location and a speed. So that makes this seem promising. Now, what forces are acting on this at any instant? I mean, if you want, if it helps, you can always draw a free body diagram to help you figure it out. We have a weight force of 19.62, a normal force from the ground, and a spring force, I'll call it Fs. Okay. All three of those are in the category of forces we can deal with. And so that makes us feel pretty good about using conservation of mechanical energy. Okay, so let's write out a table, and instant 1 is going to be when the spring is stretched 8 centimeters. And instant 2 is going to be when the spring is at its resting length. There are two conservative forces here. So we can say that the, H equals 0, let's say H equals 0 is where the object is the whole time since it's moving horizontally. So I'm going to put in the conservation of the potential energy for gravity. But what we're going to see, and I think should make sense, is if the height doesn't change at all, you're not going to have any change in potential energy from gravity, and so it's not going to affect the problem. Okay, in this case, with our h equals 0 at the height that the thing is at, we're just going to have potential energy equals 0 for both of them for gravity. So, okay, the gravitational potential energy is 2 kilograms times 9.81 times 0. So at instant 1, it's equal to 0. And now the spring potential energy the formula I gave you for spring potential energy is 1/2 times k times x squared, where x is how far you are from the resting length of the spring. So this is 1/2 times 400 times 0.08 squared and so that comes out to be 1.28 joules. And then the kinetic energy, well, we're just stretching it out and then letting it go from rest. So the speed is 0. So, this is 1/2 times 2 times 0 squared, which is 0. And so now we'll think about when this object passes the spring's resting length. So the gravitational potential energy is 2 times 9.81 times the height is still 0. So you see what I said we would see is that gravitational potential energy just doesn't affect this problem. So what's the total work done by gravity over this motion? Yeah, it's negative second one minus earlier one, which is negative 0 minus 0, which is 0. The spring, that's the one that's doing work. So this is 1/2 times 400 times x squared. What's x when the spring passes its resting length? So x is how far the spring is from its resting length. So it's just going to be 0 when it passes its resting length. And then we want to calculate the speed. So our kinetic energy is going to be 1/2 times 2 times v squared. Or if you cancel the 2's, this is just v squared. So now we'll add up the stuff at instant 1, set it equal to the stuff at instant 2. I'm going to stop writing all the zeros in there, but so we're just going to get 1.28 is equal to v squared. And so v is square root of 1.28. So 1.13 meters per second. Okay, so now I said I was going to show you how you calculate that spring stiffness. So here's a question. How could we have determined that spring constant? Well, if you hang an object with a known mass from this spring, so let's do it with the cart while we have it, it's already attached to the spring. So let's say this thing has a mass of 2 kilograms. And then you measure the X as it hangs. And so X would be how far removed it is from the resting length. The difference of the spring length from its resting length. Okay, so I'm going to just figure out some numbers that make this work. So say that we did this calculation and we measured that X is equal to 0.04905 meters. Okay, so just under 5 centimeters. That's not the length of the spring, that's the difference. That's how much the spring is stretched from its resting length. So like one thing you could do is measure the length of the spring, then measure the length of the spring when it's hanging there and subtract. Okay. So then to calculate the K value, we would take K is equal to mg divided by the elongation. And so in this case, that's 2 times 9.81 divided by 0.04905. And we get a K value of 400. So you can imagine the way this works, like if that spring is not very stiff, it's going to stretch more due to the same amount of weight. If the spring is really stiff, it's not going to stretch very much for that same amount of weight. And so this is how that stiffness is measured. Any questions about either parts of that problem? Okay, so now, yeah.
So for like this problem, it probably involves like the change of the potential energy of the spring force and the wheel look, right?
To calculate, like how does that calculation come about?
Yeah, I guess we don't need to know the.
Yeah, really, the easier way to do it is not in terms of the potential energy. It's just in terms of so it turns out that we didn't do calculations this way. But if you drew a free body diagram, you'd have this, and you'd have the pulling force from the spring, and that pulling force is equal to K times X. And so this is what you would use to, then you'd use Newton's second law, given that you've measured the X value, and that's where it comes from. Yep. Okay, one thing we're going to do in a few problems is, so this is an example of combining conservation of linear momentum and conservation of mechanical energy. So this is something we'll do anytime a problem has a part where you're relating a speed to a position and a part where there's a collision in it. Okay, so then we'll use conservation of linear momentum for the collision part and conservation of mechanical energy for the relationship between the speed and the location. So let's say we have a cart here with a mass of 0.2 kilograms. And a cart here that's initially at rest. So this one's initially at rest with a mass of 0.1 kilograms. And when they collide, they're going to latch together. And let's say that what we're going to do to start the motion of this system is think of like the start of a pinball game. We're going to pull back a spring, okay? And this spring has a constant of 600 newtons per meter. So we're going to pull the spring back um, 2 centimeters, 0.02 meters from its resting length. And release. And the question is, how fast will the two carts be moving once they collide and latch? Okay, well, we're only going to use conservation of linear momentum for the part where the collision is happening. So everything before that is going to be conservation of mechanical energy. Okay, I guess that means that conservation of mechanical energy is going to tell us how fast the 0.2 kilogram cart is moving the instant before the collision. Okay, so in all of the instants before the collision, we need to think about the forces that are acting. So what forces are acting? There's gravity, there's a spring force, and then there's a normal force from the ground. All of those are in our allowable category of forces. So this looks like a promising way to go, conservation of mechanical energy, because we're trying to figure out a relationship between a location and a speed. Okay, so our instant one is going to be when the spring is compressed before we let go of it. And our instant two is going to be, okay, so think about this for a second. Conservation of linear momentum is going to be the collision, okay? And so we're not going to use conservation of mechanical energy to go from the instant that the spring is compressed until after the collision. The conservation of mechanical energy part just goes from the compressed spring to the freely moving 0.2 kilogram cart, okay? So don't make the mistake of, that's something that I see a lot in problems like this, where someone's instant one is going to be the start of the problem and their instant two is going to be at the very end of the problem. We're just sort of going from the start of the problem to the middle of the problem, and then the end of the problem is going to be the collision. Okay? So if I choose this to be my h equals 0, is gravitational potential energy going to have any effect on this problem? No, the height isn't changing. So you can put that in there, but it doesn't. I'm just going to say that this is equal to 0 in both cases. And notice that even if I had chosen a different h equals 0 that made these non-zero, you'd be subtracting them anyways. Like you'd have it on both sides anyways, so it wouldn't have any effect no matter what you called that height. So anytime things are moving horizontally, you can leave out gravitational potential energy. Okay, so now spring potential energy at instant 1. So this is 1/2 times the spring stiffness of 600 times the compression, which is 0.02 squared, and so this is 0.12 joules. And then we're releasing it from rest. So the kinetic energy is 1/2 times the mass of 0.2 times the speed of 0 squared. So this is just equal to 0. And then second, now what's going to happen is this spring is going to be speeding up until it gets to its resting length, and then it's going to slow down from there and this 0.2 kilogram cart is going to move away from that spring. So what's going to happen is right when that spring gets to 0, x equals 0, right when it gets to the resting length, this is going to lose contact with it. And so we'll put in x equals 0 for the spring potential energy, and what that's going to do is just give us 0 spring potential energy. Okay, so so this is equal to 1/2 times 600 times 0 squared, so 0. And then the kinetic energy after it leaves the spring is 1/2 times the mass times the unknown speed squared. So that's just 0.1 v squared. But the important thing you have to remember here is that all this is just from the instant the spring is released until the mass leaves the spring. And we're just talking about the 0.2 kilogram mass. Okay, so now I'm going to put this into conservation of mechanical energy. It says 0.12 is equal to 0.1 v squared. So v squared is equal to 1.2. And so v is equal to, since this is a speed, it's positive 1.10 meters per second. So now that we have that, now we're going to do the collision. Do you remember what the rules are for when we can use conservation of linear momentum? So the rules are when the two objects are not in contact, both of them have to be moving with a constant speed in a straight line. There can't be any net force on it besides the collision. Okay, well, this is moving along a flat surface. There's no friction or anything. So this satisfies that requirement. The speed is going to be constant and it's just going to be moving in a straight line. Oh, now collision, not no collision. Okay, so before the collision, we're going to add up the linear momentum. So we have the mass of 0.2 times a velocity vector. Remember, now we have to deal with vectors here. A velocity vector of 1.10 in the x direction, 0 in the y direction. Plus the mass of the second one times its velocity before the collision. That's 0, it's just at rest. Once they collide, they latch together, so you just have a single object with a mass of 0.3. And its velocity, we know it's going to be moving in the x direction, so I'll just calculate that v. Okay, so the x equation here says 0.2 times 1.10 plus 0 is equal to 0.3 v. So v is equal to 0.73 repeating meters per second. And so this pair of carts together is going to be moving to the right at 0.73 repeating meters per second after they latch. Any questions about that? Okay, let's do one more. This is a good one because it's actually like a practical thing that used to be used. So this is called a ballistic pendulum. And the way it works is, back long before there was high-speed video, people wanted to know when they made firearms or, any kind of weapons or whatever, they wanted to be able to measure the speed, like the muzzle velocity of bullets, say. But if you don't have very high-speed video, like one frame of the video takes a picture of the gun before it's fired, the next picture, the bullet's gone, so you can't use that to measure velocities. So now you just take a very high-speed video and you can measure it with a lot of precision. But the way they used to do it is they would hang a big mass from some kind of cable, and they would fire the bullet into the mass. Say it's made out of wood or something, so they know that the bullet is going to stick into this block. And then after the bullet lodges in there, this thing swings up to a new position. Okay, and so if you measure the difference in heights between these, are you following what I'm drawing there? So you fire the bullet into this still block. The bullet hitting the block makes the whole thing swing up. And it's a lot easier to just with your eyeballs see where the thing swings up to. than it is with your eyeballs to see how fast the bullet's moving or whatever. So then once you know what the change in height is here, you can go back and use conservation of linear momentum and conservation of mechanical energy to figure out how fast that bullet was going when it hit the block. Okay. So you measure H. And then you use conservation of mechanical energy and conservation of linear momentum to calculate the speed of the bullet before the collision. Okay, so let's come up with some numbers. So let's say that the mass of the bullet is 0.005 kilograms. And the mass of the, I called that a block before, so that's not very helpful. I'll just call that the big M. Is, let's say, 1 kilogram. And the measured height H that it all swings to is 0.4 meters. So that's the difference in the height that this mass gets to before it swings back down. And we want to calculate the speed of the bullet before the collision. Okay, so there's two parts. The collision, we're going to use conservation of linear momentum, and the swing, we're going to use conservation of mechanical energy. And we have to do this problem sort of backwards from the way we're used to. So I'm going to start with the swinging motion, okay? Figure out the velocity of the block with the bullet inside of it using conservation of mechanical energy. And then now that we know after the collision what the velocity is, then we can go back again and calculate the velocity of the bullet before the collision. So conservation of mechanical energy first. And this is for the swing. Well, this is what's going to be swinging here is the combination of the block and the bullet. So the total mass is 1.005 kilograms. It's a good habit to always check and make sure that the forces are all allowable. Well, so what forces are acting? There's a weight force. There's no springs or anything. And then there's that cable force. And that cable force is non-conservative, but notice that this is swinging in a circular path, and that cable force is toward the center of the circle, so it does zero work. Okay, so this is fine. We can use conservation of mechanical energy for this. So instant 1 is going to be right after the collision. I'm going to call this my h equals 0. So the gravitational potential energy right after the bullet's lodged into the mass is the total mass, 1.005, times 9.81 times 0, so this is just equal to 0. And the kinetic energy, we're trying to calculate this speed, so we're just going to call this 1/2 times 1.005 times v squared. So this is 0.5025 v squared. Instant 2 is at the top of the swing, right before it starts to come back the way it came. So the gravitational potential energy is 1.005 times 9.81 times, what's the height at that second instant? 0.4, yep. And so for this, we get 1.05 times 9.81 times 0.4. So that's 0.3943. And this is in joules. And then the kinetic energy is 1/2 times the mass times the speed squared. What's the speed when it gets to the highest point, just as it's about to come back the way it came? 0. Perfect. So 0 squared, so this comes out to be 0. And so now conservation of mechanical energy says 0.5025 v squared is equal to 0.3943. Yes?
How'd you get 0.3943? I'm getting 3.943 for this one.
Let's see. Oh, you're right. Yes. Thank you. And so divide both sides by 0.5025, and you get that v squared is equal to 7.848. Take the square root, and you get v is equal to 2.801 meters per second. Okay, so the instant after the bullet lodges in this block, the block and the bullet together are moving at, 6 miles per hour, 2.8 meters per second. Okay, now we're going to use conservation of linear momentum for the collision. And this is an elastic collision like we're used to, an inelastic collision like we're used to, because these two things stick together after the collision. So we can do this the way we've always done these. And what we have is, before the collision, we have the mass of the bullet, so 0.005 times some velocity v0, plus the mass of the block times its velocity before the collision, which is 0, 0, it's just hanging there. And that's equal to, after the collision, a single object with those combined masses, so 1.005, times the velocity of 2.801 in the x direction and 0 in the y direction. This is the velocity we just calculated from the conservation of mechanical energy.
Would we not be like considering it at an angle?
Oh, because of the velocity that it's moving? Well, when it's hanging, okay, yeah, that's a good question. So here is what's going on. So anything that's hanging from a string, you know, moving along a string is moving in a circular path or a part of a circular path. When it's hanging, it's at this part of the circular path, and it's going to swing up to this part of the path. Okay. But down here, notice that the velocity is tangent to the path in the direction of motion. So the velocity is exactly like this. Any other questions before we calculate this? Okay, so now we have 0.005, I'm just using the x equation, times v is equal to 1.005 times 2.801. So it's equal to 2.815. And so V is equal to 563.0 meters per second. Any questions about that? Okay, so I'm just gonna, over the weekend, give you a bunch of problems like this to do, some that are just conservation of mechanical energy, and then a couple that combine these two things. And let's do the quiz.